Listo.
Okay. Bueno, buenas tardes a todos y a todas. Gracias por conectarse el día de hoy a la charla de investigación del SIMPA. Hoy tengo el placer de presentar a El Hadji Yayatol. Él es originario de Senegal. Hizo su bachillerato y maestría en la Universidad UCAT en Dakar. Después hizo una maestría en el ICTP en Trieste y un doctorado en el IMPA, con una especialización en el área de sistemas dinámicos. Y actualmente es un postdoctorando en la Universidad de Sao Paulo. Y hoy nos va a hablar un poquito sobre su línea de investigación que trata de exponentes de Lyapunov para cociclos lineales, el problema de regularidad. Entonces, ya. Nada más antes de comenzar, la charla va a ser en inglés, pero las preguntas las pueden hacer en español si quieren, o portugués, los que hablan portugués. Entonces, ahora sí, ya, todo tuyo la
Muchas
charla.
gracias, Adri. Muchas gracias. Quería agradecer a los organizadores de la charla, el SIMPA, y es un placer y un honor estar aquí con ustedes hablando charla de matemática. So, okay, let me switch in English. So today I'm going to talk about Lyapunov exponent, and let me share first my screen. Okay. So the title is Lyapunov exponent for linear cocycle, and I will be focusing on regularity problem. So the idea is not the idea is not to go to technical detail and for the proofs. So my idea is to try to survey the topic and try to discuss interesting problem that will come along the way. So let me start. So as I said, we will be talking about Lyapunov exponent, but Lyapunov exponents are objects that are associated to linear cocycles. So let me first define what linear cocycles are. So we start with a measure preserving map. What measure preserving map means? M is a, sorry, let me change it. Okay. M is a measurable space. So you start with a measurable space. Measurable space. And F is a measurable map and preserve a probable measure on M. So mu is a probable measure. Mu is a probable measure. It's the probability measure on M. So we said that F preserve mu if the push forward of mu with respect to F is mu. So meaning that if you take a measurable set in M, the measure of F inverse of E is just the measure of E. So, okay, I will also consider a measurable map from M to a subgroup of the general linear group. This is a group of D by D invertible matrices. So I will assume this map to be measurable. So we said that F is a linear cocycle. This is a linear cocycle. It's a linear cocycle defined by A over F, defined by A over small f. So this is a skew product map. So you have the space is a product M times RD, taking a vector X in M, upon X in M and a vector V in RD. So the first coordinate you apply your map F, which is here. And the second coordinate, this here is a matrix A of X. For each X, you associate a matrix A of X and you apply it to the vector V. So this is a definition of linear cocycle. And let's see, what are the iterate of F? If you try to iterate F square of XV, this is just F of X and AX applied to V, right? So we get F square of X, is F, you compose F twice, And the second coordinate, you apply a at x. So in this case, will be a at f of x. So apply to the vector a of x of v. So you can do this by induction. So for any n bigger or equal than 1, so you can see what is fn of xv. So in this situation, it's exactly fn of x. And here I will make a notation, a and x applied to v. So what is a and x applied to v? Sorry. I think, okay. A n applied, a n of x is just the product along the orbit of x. So fn minus 1 of x, product till a of f of x and ax. So this is a notation. It's just a notation. So as in dynamical system, we are mostly interested on what are the long-term behavior of this map here. What happens when n goes to infinity, long-term behavior. So this is a product of matrix. You take A at each x, you associate a matrix A of x, and you look at the product of AX along the orbit of x. So this theory started around 1960 by this theorem of Furstenberg-Kasten. The Furstenberg-Kasten. And said that if this map here is integrable with respect to mu, so there is a measurable function that is lambda plus, and we satisfy these two properties. So this is invariance, so mu almost every x. Yeah. So I mean, when you apply lambda plus at f of x, it's just lambda plus at x. So this is, and b is just the limit when you take n to infinity of 1 over n, or logarithm of this norm here is equal to lambda plus of x. So I didn't say what is the norm of a of x. So this is the space of matrices. So if you take a matrix B in GLD R, so here I'm considering the operator norm. So the norm of B is just the supremum over all norm zero vector. Norm of this is the Euclidean norm here, B of V over norm of V. So but you can choose the norm you want, because in finite dimensional space, vector space, all norms are equivalent. And so this still holds for any norm in GLDR. So, and this function here is called, just put Lyapunov exponent function. See the upper Lyapunov exponent. Upper Lyapunov exponent. The upper Lyapunov exponent. So, as you can suspect here, also we can look at the conorm. This is the operator norm. The conorm will be the infimum over all v different from 0, and you can say something about the conorm. You can put in upper. If you use a conorm, you will get a lower Lyapunov exponent function, and it is stated here. So if the integral of the logarithm of norm of ax inverse is finite, so there exists also a measurable function that is lambda minus, that I denote by lambda minus, that satisfies these two conditions. This condition here is invariance, and you get an estimate. So basically what I'm saying that is that the norm of a n of x as n large, this is approximated by x e to the n lambda plus of x. So you know that if by some reason you know that lambda plus of x is positive, so this means that this norm grows exponentially. And if lambda plus of x is negative, then this decay exponentially. And if it is 0, so this norm this matrix is like rotation. It's okay. Okay. So the main question that I want to address here is the following. So question. How lambda plus and lambda minus depends on the data of the problem. So let me just put it in quotes here. Data, I mean, how lambda plus and lambda minus depend on f and also of mu. I would like to see the dependence of this map with respect to f and with respect to mu. And also if you want with respect to a as well. So let's first see an example. Let's first an example. So the example I will start with is coming from smooth dynamical system, where I consider M to be the torus. Let's say ID. This is a d-dimensional torus. And just think about, this is just say RD quotient by ZD. And you consider F from M to M to be a local diffeomorphisms. It's a local diffeom. And so since this is a local diffeom, this means that the derivative of f exists at every point and it is a linear isomorphism. So what we know about the torus is that the tangent space at any point x of the torus of ID, this is canonically identified to the Euclidean space Rd. And if you look at the derivative, so this derivative acts like a linear map. This is, you can identify it canonically by an element of GLDR. So you take, and also the tangent bundle of the torus, just pi d. Say this is just a pi d time R, it's trivial. So you consider linear cocycle f from pi d time Rd to pi d time Rd. So at the first coordinate, you have x and a vector v. This is just apply f of x and the derivative of f at x apply to v. Okay, so this map here, f is just called the derivative cocycle. This is the derivative cocycle. So you can see also an of x. In this case, I'm calling this map here to be a of x. So an of x is just given by the chain rule formula, the derivative of fn at x. And this is given by the chain rule. So the main feature that I use here about the torus is that the tangent bundle is trivial. Okay. So this construction can be done in any parallelizable manifold. So, okay, so, okay, you can also ask the question of lambda plus, lambda minus dependence of lambda plus dependence on the data, on f. And in this case, a is the derivative of s, that's enough to take f. So you can put a probability measure here. It could be the volume and all. So it's more like, so let me first state a theorem due to Magnier and Bocquet. So the theorem said that if you consider let's say let M be a surface, a compact surface, be a compact surface. Compact surface. So this is a two-dimensional manifold. So you take F to be a diffeomorphisms of class C1, volume preserving, that preserves the volume M. So recall that F preserves a private measure if it satisfies this. So in this case, F preserves the volume M. So the theorem said that if F is a diffeomorphism that preserves volume, so you have a dichotomy. So the dichotomy is the following. Dichotomy. So answer, you have F is uniformly hyperbolic. Uniformly hyperbolic. Hyperbolic. And B is, or there exists a sequence of diffeomorphisms, Fk, volume preserving diffeomorphisms of M that converge, Fk converge to F in the C1 topology. And the Lyapunov exponent of this Fk with respect to the volume here is 0. So this is a very interesting and nice theorem due to Magne and Boki. So let's try to understand what is happening here. So what is happening is that if you start with a volume preserving diffeomorphisms on a compact surface, so F is a very special type of diffeomorphism, which we call uniform hyperbolic. A uniform hyperbolic means that at every point X on the compact surface, the tangent space split in into sub-bundles. So you have a stable sub-bundle and unstable sub-bundle. So the tangent space at M split into stable and unstable. Sorry. So vector in the stable bundle are uniformly contracting, and vector on the unstable bundle are uniformly expanding. This uniform hyperbolicity mean here, or sometimes it's called annals of diffeomorphisms. So annals of diffeomorphism. So one property of these diffeomorphisms is that it is known that if F is a uniform hyperbolic, then the Lyapunov exponent associated to F is positive. So since there is a bundle that is uniformly expanding, so the norm, if you look at the norm restricted to the bundle, the growth is exponential. So norm here, growth exponentially. And if you are not uniformly hyperbolic, so you can be approximated by diffeomorphisms in the C1 topology that has Lyapunov exponent 0. So assume that if F is not uniformly hyperbolic, and if the Lyapunov exponent of F is positive, so F is a discontinuity point of the Lyapunov exponent. F is discontinuity point, is a discontinuity point. Continuity point for lambda plus, because you can approximate F by diffeomorphisms having 0 Lyapunov exponent. So one more comment about uniform hyperbolic is that for surfaces, the only surface that admit uniform hyperbolic diffeomorphisms is the torus. So only the torus admit this kind of diffeomorphisms, P2, admit compact surface, compact admit Anosov, only P2 admit Anosov. So if you start with a manifold which is not the torus and having positive Lyapunov exponent, then it is automatically a discontinuity point for Lyapunov exponent. So this is very interesting theorem, and that give us some hint about the regularity of Lyapunov exponent in this case of derivative cocycle. Any questions? Okay, so let me continue. So The other example here I will be talking about is a random product of matrices. So this example comes from probability theory and stochastic process, but probability theory, stochastic process. So I will start with, I will take M to be the GLDR to some power. I mean, I will take the space of sequence in GLDR. This is just space of alpha K, sequence K in Z, such that alpha K is in GLD for any K in Z. Very well. And I consider a map. I take a map F in M from M to itself. So this is a shift map. So what the shift map does is that if you have a sequence alpha K in Z, so you shift it 1 unit to the left. So you just look at alpha K plus 1 K in Z. So there is not a lot of difference in here. I'm just changing the position. So for instance, if you start with, let's say, some alpha here minus K until alpha 0, alpha K, and so on. So this is the 0 of positions here of the sequence. And what the map F does here is just, instead of alpha 0 here, you get in the same position, here you get alpha 1, you just shift it 1 unit to the left. And here you come with alpha 2, and here alpha K plus 1, alpha K, and so on. And here you have alpha 2, alpha minus K plus 1, and so on. So I just push 1 unit to the left. This is called the shift map. And if I take a probability measure, mu, a probability measure, probability measure on GLD, GLDR. This is a probability measure on GLDR. I can consider the product measure on M. So this is the product measure on M. This is the Bernoulli measure. The Bernoulli measure. So it is known that F preserves mu. So this is the result from ergodic theory, that F star of mu is equal to mu. So what we get so far is that you have your space M and your dynamic system here, F, the shift map, and we have also a measure that is preserved by F. So this is a measure preserving map. And I will consider A, this is from M. Sorry, I need a map from M to GLDR. So it is very easy to guess what the map will be, since this element here, if I take X here, these are sequences. You just project. Yeah, I will project to the 0 coordinates, alpha 0. And the associated linear cocycle F is defined by this map here to M time RD from X, V. Remember that X is just a sequence. Alpha K is alpha K, K and Z. And the first coordinate, you have f of X. And the second coordinate is that the projection, so alpha 0 apply to V. Okay, let me continue. So here, I have to remove these things here. Sorry. I don't have enough space. Okay. So what we get so far is that you have your linear cocycle. So let's look at the iterate of this map here. What happens if we take the kth iterate of F? So the kth iterate of F, let me say the nth iterate of F. Okay, this is just the first coordinate, so you're applying the shift map, which is fn of x. So this is a sequence alpha k in z. So the image here is just alpha k plus n, k in z. So you shift n unit to the left. And what remains here is just the product of the n first element of the point x. So you take alpha 1, alpha 0, apply to v. So this is called the random product. This is a possible value. This is the all possible values of some random product of a random product, a random product of matrices, product of matrices, more precisely given by the support of this measure, support of mu. So I think it is a little bit abstract putting in this way. So let me just, to fix idea, let me just tell you what I'm really doing here. You assume that you have two matrices, A1 and A2. So you have two matrices, A1 and A2 in let's say in GLD R. So you put two numbers here, P1 and P2. And for us, P1 is the probability of choosing A1 and P2 is the probability of choosing A2. So what I'm looking here, the measure that I'm associating here is given by P1 delta A1 plus P2 delta A2. So for instance, if P1 is equal to 1/2 and P2 is equal to 1/2, what is really going on here is just like the situation where you flip a coin, the coin toss situation. So as two outcomes. So either you have a tail or you have a head. So let's say if it is tail, you choose A1. If it's head, you choose A2. So what you do with the choice, you multiply your choices. So let's say you multiply all the choices you get from this process. Let's say you toss n time this coin, so you get a n minus 1 till ai 1 and ai 0, and so this is the random product of A1 and A2 according to this distribution. So P1 is the probability of choosing A1 and P2 is the probability of choosing A2. So in the situation where all this P1 is equal to P2 equal to 1/2, so you get exactly this the coin toss situation. So the question here I'm asking is how lambda plus and lambda minus depends here. Sorry. It depends on A1, A2, P1, P2. In other words, how it depends on this measure mu. How it depends on mu, the measure mu. Okay, we see in the case where we are dealing with diffeomorphisms on the on surfaces, we get a result due to Magne-Mbocchi. We almost get except in the situation of uniform hyperbolicity, so you get a discontinuity point. This is the first n. This second n is the case of random product matrices. So here we get very nice result. But before stating the results, let me just give an example where you still get discontinuity. So let's say I choose A1 to be this matrix 2, 0, 0, 1/2, and A2 is equal to be let's think, okay, 0, 1, minus 1, 0. This is a rotation of 90 degrees, rotation of pi over 2. So these are matrices in SL2 R. And let me consider T in say 0, 1. And I consider measure mu t to be equal to 1 minus t, the Dirac mass at A1, plus t, the Dirac mass at A2. So let's say if t, let me just say if t is equal to 0, what happened is that mu 0 is just the Dirac mass of A1. So in your process, you only choose the matrix A1 because the probability of choosing A1 is always 1. So you only choose the matrix A1, and we know that the norm of A1 is 2. So the lambda, the Lyapunov exponent, the associated Lyapunov exponent for mu 0 is logarithm of 2, this case. So, and if t is different from 0, so meaning that this never vanished, this never vanished. So there is a positive probability of choosing A2. And we know the action of A2 is just exchanging the horizontal and the vertical direction. So it maps the horizontal direction to the vertical one and the vertical direction to the horizontal direction. So let's say you choose A1 n times. So what A1 does is that it stretches the horizontal direction by a factor of 2 and contract the vertical direction by a factor of 2. So if you choose A2 reverse exchange the direction. So what was expanding here become contracting, and what was contracting become expanding. So you can prove that lambda plus in this case is just 0. So you see the limit when t goes to 0 of lambda plus of mu of t is different from mu 0. Lambda plus is different from logarithm of 2. Is different from this here is different from lambda plus of mu 0, which is logarithm of 2. So to make the picture, what you will get is you have 0 here, and this is the t-axis, and this is the lambda plus axis. So at 0, you get logarithm of 2. And for t different from 0, you are here. So 0 here is a discontinuity point. So this is a discontinuity point. It's a discontinuity point for the Lyapunov exponent. So very well. So let me state, this is a very particular, this is a very special situation because I am putting two matrices, A1 and A2, and and in the first choice, I just exclude A2 and only choose A1. So, and if I'm far from 0, if I'm far from the origin, so this curve here is well behaved. It is even smooth. So you have only constant 0. So the first result in this direction is due to Furstenberg-Kiefer, theorem of Furstenberg-Kiefer. Furstenberg and Kiefer. I think this is around 1983. It stated that if the cocycles, if the cocycle is irreducible, I will explain what irreducible means. Then Lyapunov exponent is continued. Then the Lyapunov exponent of exponents are continuous functions. continuous functions. So this is an algebraic assumption, what means that you are not in this situation. If you are far from the previous situation, you get continuity. So continuity means irreducible means that there is no subspace, proper subspace of RD AX at L is equal to L for mu almost every X in M. So if this holds, so if there is no proper subspace of RD satisfying this, so you get Lyapunov exponents are continuous. Okay, and let me state a similar theorem in this situation that removes these conditions. So this is due to Becker and Marcelo Viana. This was around 2010. I think it's published in 2017. Published in 2017. So it said that if you fix A1, A2 till AN in GL2, here, this is for any dimension, D. This is for any dimension. Any dimension. On the irreducibility condition, you have continuity. But for in dimension 2, GL2R, and you take P1, P2 till Pn, these are PIs are positive, and the sum of the PI is equal to 1. PI is equal to 1. Then if you have A1I till A and I, a sequence of matrices, this converging to A1, this converging to AN, and P1I till PNI, both this converging to P1 and converging to Pn, so on. Then the associated Lyapunov exponents are converge as well. So what I mean is that the lambda of mu I converge to lambda of I. Sorry, lambda of mu is plus or minus, where mu I is just sum I from 1 to n of P, sorry, here j from 1 to n of P ji delta A ji. And mu is a standard one, sum j from 1 to n of Pj delta Aj. So what I'm taking here is that measure with finite support. For measure with finite support, well, each PI are positive, so you get continuity. And this still work if you replace this by still true for measures with compact support. For measures with compact support. With compact support. So, but in dimension 2, and what happened in higher dimension? This is announced. This is a result by Avila, Viana, Eskin, Avila, Eskin, Viana. What we get is that they announce that it's still true. Still true for any dimension. So without this condition here, without the irreducibility condition, but we are not allowed to take P. This is, let's say, if you have P1, this is P2, P1. We are not allowed to take P2 to be 0. So with what happened in this situation? So here you are allowed to take P to be 0. So but in the theorem of Becker-Vienna, so the PIs are all positive. So this is the main difference. So any questions? Okay, let me see how much time do I have. Adri, can you tell me how much time do I have?
You have 10 more minutes.
10 more minutes. Okay, let me just state. So what happened for higher regularity? Can we get more regularity? More regularity. So let's say, can we prove instead of continuous, can we prove, let's say, Holder or Lipschitz or even differentiable? Okay. So let me first answer this question. So this the theorem by myself and Marcelo. This was in 2018, and we published this in 2000. It's now available in IMS 2020. So what we prove is that for in dimension 2, so Lyapunov exponents are Holder continuous. So for any probability measure with compact support, for any probability measure with compact support. Okay. Measure with compact support. So this is very important. If the support is not compact, you cannot. I mean, there is a result by Adriana Sanchez, who is here, and Marcel that said that if the support is not compact, you can hop. You cannot hop to get continuity even. So the best thing you can get is semi-continuous. So in this situation, you have to assume compact support. And before this result, we have also another result by the Yuval Perez that motivates this works. This is not Perez, but Lepage. This was around 1987. And what Lepage proved is that Lyapunov exponent, if the cocycle is, is irreducible and contracting, I'll not explain what is contracting, but contracting. So then Lyapunov exponent, the top Lyapunov exponent is Holder. Okay, this was before. What we did is we just try to remove this hypothesis, irreducibility and contraction, to prove we still get Holder continuity. But again, in this topology here, that is the PI are positive. So the topology, basically, what the topology that you are looking here is that you say two measures are closed if they are closed in the weak star topology and the support of the measure are Hausdorff closed. So that's why I'm only taking compact support. So if you look at the space of compact subset of GLD, so there is a natural topology, which is the Hausdorff topology. So two compact sets are closed as Hausdorff closed if you can put one compact set in an epsilon neighborhood of the other and vice versa. So and this topology is metrizable, and when you metrize the topology, so you can properly state this theorem. So you get a Holder continuity with respect to that metric. Okay, so before just explaining what are the tools used to prove this theorem, let me just state one more theorem. This is a result due to Yuval Paris. And I think it is, I think it's in 1991. So what this theorem said that if you fixing the matrices A1 till AN, if you look at the map that associate from RD positive to R, given P1, sorry, Rn, P1 till Pn. So you look at the Lyapunov exponent associated to the measure mu, which is just sum 1 till n of Pi delta AI. This is real analytic. The difference between this theorem and this here, we are allowing to vary all the matrices. But here, when you fix the matrix and you just look at the probability associated to each matrix, and you look at the Lyapunov exponent as function of this probability measure, so this is a real analytic. And recently, with this theorem, this will come by myself, Adriana Sanchez, and Jamerson Becerra. We were able to extend this result of Perez. Yuval Perez result can be extended. For cocycles, for random product of quasi-periodic cocycle, for random, instead of random product of matrices, but here we are taking random product of quasi-periodic cocycle. Quasi-periodic cocycle. So, okay, this is kind of survey of what has been done in this topic. So just focusing on the regularity problem. There are also other questions that are very interesting. Let's say the positivity of Lyapunov exponent and so on. But here I'm just focusing on the regularity problem. So let me just explain one of the tools used to prove such kind of theorem. So tools. And one of the most important tool is due to Le Drapier, this is a representation of Lyapunov exponents. Representation of Lyapunov exponent. So basically, what it says that you can make a one-to-one correspondence between Lyapunov exponent and invariant measure in projective space. Invariant measures in projective space. So remember, we have a cocycle m time RD, where you have mu is the measure defined on M. So you can look the associated projective cocycle PF. This is just the projective version of this. So given M, then M time PRD, and to itself, given upon X and a representative V. So you associate it to f of X, and as the second coordinate, AX applied to V. So invariant measure, I mean invariant with respect to this projective cocycle. So those measures will be called stationary measures. Stationary measures. And let me say few words about stationary measures. So let's say, okay, if you consider a map phi, let me consider this map defined from M time PRD, RD to okay, to R given a vector upon X and a vector V representative. So you can look at the logarithm of the norm of AX applied to V over the norm of V. So the Furstenberg theorem said that Ladrapier, that this is the maximum, the Lyapunov exponent is just the maximum of the integral for m times PRD of the logarithm of this function. So it is easier to deal with this than dealing with the asymptotic behavior of norm of A and of X. So V, the mu of X, the eta of V. I will explain who is eta. So eta stationary. So eta stationary. And this maximum is over all this eta, and maximum is always attained. Max is attained. So there are measures. There is a measure eta that I can call eta max, such that this lambda plus of mu is given by the integral of m times PRD of the logarithm of AX V over norm of V, the mu of X times the eta max of V. These are measured on PRD. These are probability measure on PRD. So how these are probability measure on PRD, and you said that a measure eta is mu stationary, is stationary with respect to the measure mu if it is a fixed point of the Markov operator. So I don't want to go to the detail, but basically what is that? Is that let's say P star eta is equal to the integral of AX push forward of measure eta with respect to X. So sorry, but this is eta. And if eta is mean that for any measurable set E in PRD, the measure of E is this integral over X of eta of AX inverse of E d mu of X. If a measure satisfy this equation, so we said that it's a stationary measure, and Lyapunov exponents are given by this stationary measure. So to prove continuity or Holder continuity of the Lyapunov exponent, it's enough to prove the regularity of these measures, the regularity of this stationary measure. So when you assume that your cocycle is irreducible, so this stationary measure is unique. So you don't have to worry a lot about, okay, if you have a sequence of measures that converge to some measures, so this measure will automatically be a stationary measure and it will realize the Lyapunov exponent. So when the cocycle is irreducible, this set is just one element. But when the cocycle is not irreducible, so you are in trouble because there are a lot of stationary measures. And the stationary measure, the set of stationary measures is a convex set. So you have to localize which are the measures that realize the Lyapunov exponents. So this is the main difficulty, and you prove that using some argument that we call the energy argument that was developed by Avila, Eskin, and Viana, and that gives the proof. So if you have questions, you can ask. Adri, how much time do I have?
None.
Okay, so I think it's a good point to finish. I'll stop here, and if you have any questions, so I will be very happy to answer.
Okay, thank you, Yaya. Gracias a Yaya por la presentación. Tenemos un par de minutitos, tal vez, si alguien tiene alguna duda o algún comentario. Bueno, tal vez, ya, a lo largo
Okay.
de la charla,
Uh-huh.
vos mencionaste,
Okay.
bueno, ejemplos sobre la dependencia con el cociclo y con las medidas, pero en los últimos resultados siempre se trabaja con la misma dinámica en la base, ¿verdad? Que es la
Sí,
del producto
exacto.
aleatorio. Bueno, el shift.
Sí.
¿Podrías mencionar un poquito cuál sería la dificultad si queremos usar otra base?
Uh-huh. So, okay. Deixa eu vou compartilhar. Ecrã. Okay, let me just. Okay, so as you said, I'm always considering, I'm always fixing the map F from M to M. This is, I always fix this to be the shift map, system map. And one, I didn't say it, but okay, let me just, and I was taking M, GL, DR. And one of the feature of these things is that this only depend on the zeroth coordinate. This only depend on the zeroth, on x0, on alpha 0, or x here. I mean, you take a of x. So what I'm doing is just projecting to alpha 0. So Adriana, you are asking that I'm always looking the dependence of Lyapunov exponent lambda plus with respect to the measure mu, right?
Exactly.
Okay, so here you can look at, as long as you assume that your cocycle is locally constant. Your cocycle is locally constant. Locally constant meaning that it only depends to the zeroth coordinate. You can look at the Lyapunov exponent with respect to A, but you always can conjugate it to cocycle in this way, which is the projection. The projection. So there is always a conjugacy between, and this is a very particular type of cocycles between locally constant cocycles, constant cocycle, and the random product case, random product of matrices cases. But if the cocycle is not locally constant, so okay, there are also classes that I didn't mention. For instance, you have a fiber branched cocycle, so you still get continuity, and you can still vary F if it's fiber branch, and you still get continuity. But if the cocycle is not fiber branch and it's not of this type, so we don't know exactly. We don't know what happened. And for instance, varying the cocycle. One of the concrete example that I can give is that look at, for instance, F from M to M, which is the M, where M is the compact surface. The example of Magnier. So here I'm not looking the dependence with respect to the measure. Here I'm fixing the measure and I'm looking the dependence with respect to the diffeomorphisms. Here I'm looking lambda plus of F. And in this particular situation, so you don't get continuity. You don't get continuity unless you are uniform hyperbolic. You're uniform hyperbolic. If you're uniform hyperbolic, you get continuity. If you are not a uniform hyperbolic, so if you have positive Lyapunov exponent, you can always be approximate by diffeomorphism having zero Lyapunov exponent. And one of the difficulty to prove this theorem is that when you perturb F, so you are still perturbing the derivative. So you can, if you perturb F, you can get G. The derivative is always perturbed, also perturbed. hope that I answer your questions.
Yes, thank you.
Welcome.
Si no hay ninguna otra pregunta, entonces agradecerle a ella por participar en el coloquio de investigación del SIMPA y de nuevo a todos ustedes por presentarse. Antes de irnos nada más, queríamos tomar una foto de los y las participantes. Entonces, ya si podrías dejar de compartir, por favor, para que aparezcamos todos. Y si pueden, sí, ya está, perfecto. Y si pueden prender las cámaras, por favor. Bueno, los y las que gusten.
Adriana, ¿tienes la cámara apagada?
Ah, mira, sí. El problema es que mi cámara...
Ya. ¿En qué año estudiaste en el ICTP?
Okay. Fue en 2012.
Yo salí del ICTP en el 98. Ojalá que un día lo podamos tener por aquí junto con Jenny.
Ojalá sí. Después de esa pandemia y todo.
Mira, Rafa, no lo había visto. Rafa.
Yo creo que ya estamos todos, ¿verdad?
Solo te veo a vos, pero yo creo que es por la forma en que estoy compartiendo pantalla. Vamos a ver. Yendo a la pantalla, galería, sí. Listo, ahora sí ya.
Ahora
bueno.
Sí.
Rafa.
Bueno, Catalina está ahí también.
Mari, vos nos avisas. Para
listo, sí. Entonces a la 1, a las 2 y a las 3. Muchas gracias. Que tengan linda tarde.